All right, so let's get started with the backside of stoichiometry 5, acid base, and let's get at it. So what volume of a 0.050 molar nitric acid, okay, solution is needed to neutralize a 0.075 liter of a 0.065 molar barium hydroxide solution? So it should be clear, party people, that we're dealing with a strong acid. Notice the nitric acid, ic becomes 8, so that's the nitrate ion, that's -1, therefore you need an H. And then we have, this guy is a what? A soluble, or I should say a group 1 or a group 2 ion with a hydroxide. Now, exception to that is magnesium, but barium is not. And again, if you weren't sure about that, go to your solubility rules, and barium hydroxide is soluble. So this is a strong base. So we have a strong base, and we have a strong acid. So they're asking how much of this acid is needed to neutralize. Now, neutralize just means that all of the protons that are given from this, okay, acid will react with all of the hydroxides that are produced from this base. That will, of course, become water. We all know that this reaction of producing water is a one-way reaction, okay, because the other way, Kw, is so small, so it spontaneously makes water. So essentially, we're trying to match all the protons from the acid to the hydroxides of the base. This is stoichiometry. And because it's a strong acid, strong base, there's a completion reaction going on here. Now you may say, what about the H pluses that are in water? Remember, those are in such small concentration, they're not significantly they're not significant compared to these concentrations. Remember, water naturally does this a little bit, right? It does break apart a little bit, but these concentrations of protons and hydroxides are so much larger. This little value by water doing it, autoionization, is insignificant. So let's do this. So I'm trying to figure out how much of nitric acid in terms of liters do I need to match all the H pluses with hydroxides. And that's important, party people. That is the stoichiometry, that the proton from the acid plus the hydroxide from the base makes the water. In this case, we say this is the net ion reaction because it is a strong acid, strong base. And I know that we're not dealing with a lot of strong acids, strong bases in chemistry or organic chemistry, but I'm starting you with that nonetheless. So from our precipitation or molarity unit, we should recognize that, wait a minute, I've got a molarity and I've got a liter. Yeah, you can get moles of hydroxide or barium hydroxide and then get hydroxide. Remember, there's a ratio of hydroxides to barium hydroxide. So I can do that way. Remember, molarity is equal to what? Moles over liter. Well, you have your liter, you have your molarity, you can solve for the moles of the barium hydroxide. Notice there's 2 hydroxides per one of these, so you should be able to figure out what you have to do there. And once you have the hydroxides, that's a 1-to-1 ratio, you've got the moles of nitric acid. So I'm going to do this dimensional analysis. The dimension analysis is what I'm going to use to do this, but you could certainly break it down into steps. So let's be crazy and get started. So I'm going to start with my 0.075 liters, and I'm going to times it by my molarity. Now, of course, this is barium hydroxide. All right, so I'm going to put barium hydroxide over here, BaOH2, to know what I'm dealing with. And I'm going to times it by the molarity. The molarity is 0.065. Now, really, it's 0.065 moles over 1 liter. And notice I'm in liters. So you can see pretty clearly, liters cancel, and I've got moles of barium hydroxide. But, party people, be careful. This is what we call a dibasic compound. It produces twice as many hydroxides as its formula. So what do I know? For every 1 barium hydroxide, and here we come with stoichiometry, mole ratios, there are 2 hydroxides. And so now I get total hydroxides. Barium hydroxide goes bye-bye. And then, because, well, let's keep changing inks because it's fun. Then, what do I know? Well, for every 1 hydroxide, there is 1 proton. Okay, what's the whole point of the problem? We're trying to work backwards to see what the volume of the acid. Now, in truth, okay, if I really wanted to be technical, just to show you, Okay, I am jumping the gun a little bit, but again, I can do that. Okay, for every one hydroxide, there's one what? HNO3. Now, of course, I could have kept one H plus here just to make sure you see that. So that goes bye-bye. And of course, if you want to, you don't have to. For every one HNO3, there's one H plus. Now I kind of circumvented that by doing the H plus here, but be careful. There could be acids out there that are what we call diprotic. Like for instance, okay, we have H2SO4. Okay, so you got to be careful. So I just did this extra step here. You're right. One nitric acid produces one H plus, so I'd be fine by putting one H plus here like I did, but just be careful. Okay, and again, easy place to get things wrong. So use your chemicals in your units. So nitric acid goes bye-bye, and now I've got moles of H pluses. And again, I could put the H plus here and the nitric acid doesn't matter. So in any case, I've got moles of my proton or mole of my acid. Okay, and if we do that, 0.075 times 0.065 divide by 1 times by 2 divide by 1 times by 1 divide by 1 times by 1 divide by 1. Okay, I know you don't really need this mathematically, but you do need this to understand and catch yourself in a possible scenario where you're dealing with a diprotic acid or a monobasic. These ratios can be different, so you've got to watch, okay, the acid and bases. You can't assume it's 1-to-1. All right, any case, when you do all that, you get 0.00975, and this is of course moles of the acid. And you can say H plus, H3O plus, it's all the same. Okay, it's the moles of the acid, and that's the acid there. All right, now what do they want? They want the volume. Well, what's the volume? Well, molarity is moles over liter. Okay, we know the molarity is 0.05. We now know the moles, 0.00975 moles. Solve for the liters. Okay, when you do that, okay, rearrange it. What liters is equal to the 0.00975 moles. Okay, over the molarity, which is 0.05. And what is molarity? Isn't it moles over liter? And if you look at here, party people using your units, I know I'm getting crazy. The moles cancel and you get 1 over liter, which is the same thing as liter, right? So 1 over liter gives you the liter unit. And when you do that, you get a volume to be 0.195, and that's liter. Okay, and that basically means 195 milliliters of 0.05 nitric acid is needed to neutralize that. Now, there are people in other courses that may say, hey, Mr. Grodsky, isn't this the titration formula? Couldn't I just do MV equals MV? And for those that don't know what I'm doing, MV of the acid equals MV of the base. Well, this only works, okay, if the moles are equal, right? Because we were dealing with an acid that was HNO3, and we're dealing with a base that was dibasic, it was barium hydroxide. This has twice the OHs. So if you were to if you plugged in, hey, what volume do I need? That's your X. This number we had, right, 0.05. We had the volume of the base 0.075, and we had the what, molarity 0.065. We would solve for the volume incorrectly if you plug those numbers in, unless you put this 2 here, and I'm just not a big fan of that. Okay, some teachers will teach that. I hate that. You don't know why the 2 goes there. Could easily get that wrong. Okay, to completely understand this, you should be living in this land right here. Okay, dimensional analysis. So that's number 1. Let's go on to number 2. Okay, number 2, let's read the blurb. Industrial wastewater often is contaminated with strong acids. Okay, environmental regulations require that such wastewater be neutralized before it is returned to the environment. That means we want to make sure that we take something with a very low pH and raise it up close to what? Neutral before we return it into a body of water, because a very low pH or very acidic water would kill life as we know it in those little bodies of water. Okay, so we have 1.5 times 10 to 2 milliliter sample of wastewater was titrated. Now, what does titration mean? Titration means that we are taking a known amount of some chemical and we're going to figure out what the other chemical's value is from a known amount. We've done this gravimetrically, right? We've done it with, hey, what is the formula of a hydrate if I know the mass of the anhydrate and the mass of the regular hydrate, the missing water. So we're going to knowing how much water was missing, we can figure out the percentages. That's a gravimetric titration. Or precipitation analysis is a titration where knowing the moles of the precipitate, we can work backwards to figure out, okay, the moles and eventually the grams of the reacting compound. So we've done titrations where we've used information about one chemical to get another. Here it's volumetric. But in any case, getting back to it, we take a sample. It was titrated with a certain known concentration of sodium hydroxide. And we take a certain milliliters of base was required to reach the stoichiometric point. Now, what this means was we took a known amount of the wastewater. So they gave me 1.50 times 10 to the 2 sample of wastewater was titrated. So we took the wastewater, okay, and I guess it's 150 milliliters. They just put a fancy way to put this here. So 100 milliliters of basically the acidic solution that has strong acids in it. So that's that. And then we're going to deliver, usually by a burette, okay, to understand the problem here. We're going to deliver the base, okay, and we have a known amount of base, 0.1250 molar base. And of course, that base is a strong base. How do I know? A group 1 ion, Na+, with a hydroxide, that is a strong base. It's completely soluble, so you can produce a lot of hydroxides. Complete dissociation. And what we're saying is we dropped enough base in this so that we stopped the titration once we reach the stoichiometric point. Now, what's that point? That's where the OH minuses from the burette, okay, drops of Jupiter, right? These little drops matched up with all the what? The H pluses, or the H3O plus. Okay, in this case, I just drew a 1. So we matched up all the OHs in the burette that dropped in here with the H pluses. Now, we know we reached the stoichiometric point in lab when our indicator changes, and that's really called an endpoint, but we'll talk about those specifics later on. So we know that we're going to basically stop the titration where the hydroxides equal the H pluses. And if we know how much hydroxides we delivered, we know how much H pluses were in the solution. That, my friends, is a titration. Okay, that's exactly what we're going to do here. So in order to know something about this chemical, how much moles or how much particles of OH were delivered? We know it stopped when they equaled. So how much was delivered? Well, guess what? My starting point here is going to be the volume, okay? And so I delivered, okay, 8.65 milliliters of the base, NaOH. Okay, now I'm going to convert this to liters because I'm going to use molarity to get to moles. Now, if you don't like what I'm doing dimension analysis wise, what you could do is convert this to liters and times it by the molarity. We should know that liters times molarity gives me moles. I'm just doing it here because I love dimensional analysis. So I'm going to get rid of, I know that for every 1,000 milliliters, there's 1 liter. Okay, so I know that the milliliters cancel. I know that makes this 0.03865, but hey, I'm tall. Now, once I have my liters, I'm going to use my molarity, and this should look familiar to us because we've done this before with molarity stoichiometry worksheets we've done. Okay, so what was the concentration? 0.12. So hold on, for every 1 liter, there must be the ratio of 0.1250 moles. Looky here, I'm using the molarity as a what? As a converting factor. Liters go bye-bye, and what do I have? Moles of NaOH, or hydroxide, because it's a 1-to-1. Now, what's the next part of this? Now they have moles of my base, okay, which is really the hydroxide, and you can get crazy with this, but so for every 1 NaOH, there's 1 hydroxide. Okay, I did it. I got crazy. Okay, so I got moles of hydroxide. And what do we know? In volumetric acid-base titrations or neutralization, it's always going to be, for every one OH minus, there's one proton or one hydronium ion. And what's that going to give me? Moles of H pluses. Go find that number. So we do 380.65 divide by 1,000 times 0.1250. Okay, essentially times by 1. That's all the ratios there. And again, it seems like I'm doing a lot of work here to get to 1, but it's definitely good checks, okay, to make sure you're thinking correctly. And what I get is 0.00481, and that's moles of H plus. Okay, what do they want? What's the molarity of the hydronium ions? The hydronium ions are synonymous with H+. It's the same thing. So I have the moles of the H+ of the hydronium ions. They want the molarity. Okay, so what's the molarity of the sample wastewater? Now careful. They're not saying what's the molarity after I added the compound. They want the molarity of the original. That's really important. The original. Okay, we're going to see this in the lab. It gets a little confusing. The original. Okay, and I can do this. After I've added the stuff, we've still matched these guys up, right? This happens in the Stoich problem, okay, right here. So we know that this solution had that many moles of H pluses. What was the original solution? Well, it was 0.150 liters, and that's all I'm doing there. And then, of course, molarity is what? Moles over liters. I converted this original solution to 0.150 liters. And of course, when I get that, the answer is, okay, I'm sorry that W is silent in answer. Answer is 0.0322 molar. And of course, that's equal to the H3O plus concentration, which is the same thing as the H plus concentration. All right. And you notice we didn't need to know that what the acid actually was. Okay, we just had it was in there. So that's how we do that. And again, the math isn't difficult, but all the little things I talked about here are very important. We're going to go to lab this next week, and this is going to be very helpful. So in any case, that's the answer. Okay, number 3. Okay, so number 3. A silly biochemist needed to standardize a solution of KOH. Now, KOH is a strong base. We should all recognize a group 1 ion with a hydroxide strong base. Completely dissociates. The problem with strong bases, and the reason we use them, is that a strong base, as I said before, with a weak acid will stoichiometrically drive the weak acid okay, to completion, because a strong base will pull the proton from them. As long as I have enough strong base, it's a limiting, okay, it's enough to pull. As long as there's more of the strong base in the weak acid, or at least the same amount, I can make the weak acid completely dissociate into its conjugate base. That would normally never happen, but that's what we do a lot of. We're going to take this weak acid. Now, the acid that we're going to talk about today is called potassium hydrogen phthalate. We call it KHP. And it's what we use to standardize solutions, because the problem with dealing with a strong base, to do titrations where we, again, drive a weak acid to completion and do calculations of how much was it there and so forth, the problem with strong bases, because of their high reactivity, they often react with other things in the air. One of the things that hydroxides react with is CO2, and they make carbonates. So over time, okay, a strong base, okay, can react with the carbonates in the air. Also, we've learned also that CO2, if I have a solution of strong base that's sitting out, okay, whatever that might be, in this case it's KOH, we've learned that CO2 in the air can hit that and lower the concentration. So there's all kinds of issues regarding strong bases, and just the fact that CO2 in the air is going to drop the pH of this solution and make it feel like it's a weaker solution than I made. Meaning I could make 0.5 molar in the lab, and it could be out for a day, but before I use it, I want to make sure what its current molarity is, so I test it with KHP first. And I'll probably find it to be like 4.7 or something, because it does react with other things. And I need to know, if I'm doing a titration, I need to know exactly what the concentration is of my base in order to find exactly what the weak acid concentration was if I'm doing that type of analysis, okay, as we're going to do in lab. So party people, I've got to test it before I use it. And we use it with something called KHP. Now, KHP is something we're going to use. There's something really special about KHP. Number one, it itself is a weak acid. Two, all right, because it's a weak acid, it has no reactivity with things around it. So therefore, whatever we measure, we definitely know its concentration. And another thing, because it has a high molecular mass, a lot of grams per mole here, what can happen, party people, is that if I was to be off by a few grains, okay, or a little bit off in my mass, it's not going to affect the molarity as much because the molecular mass is so big. Think about it. If something was 2 grams per mole and I'm off by a gram, boy, my molarity could be cut in half, or my moles can be cut in half. But if the molecular mass is 204.22 and I'm off by a gram, boy, I'm off by what? 1 over 204. Not much of a difference there. So I have room for a little bit error here. It doesn't react, and I can say with really good confidence exactly what this is. It's a dry chemical, doesn't react with the air, it's not being diluted or evaporation due to water, all kinds of issues. Remember, a solution of strong base, the aqueous water could evaporate, which could increase its concentration. The CO2 can react with the water to make it acidic and change its concentration. It could react with the strong base directly to make it carbonate, all kinds of issues. All right, so to do this titration with a solid piece of acid, okay, what we're going to do is we're going to start with the acid. So basically they took 0.674 grams, okay, was discovered in 100 milliliters of water in a drop. So they put this in a drop of water, okay. The solution was filtered, was titrated with KOH, the titration required. So they're saying that I took some dry grams of KHP, that's potassium hydrogen phthalate, okay, and I took, basically dropped that and dissolved that in 100 milliliters of water, okay, or made a 100 milliliter solution, and it dissolved because it is soluble. And then essentially, okay, I put up my burette, which is our device that will drop, it's not a very good burette, but hey, it's going to drop my base. So this has my KOH in it, strong base, and the strong base will what? Will pull H's stoichiometrically from this weak acid. Pretty important. And we found that we added how much? We added 41.7 milliliters of the base was needed. But I don't know the concentration of the base. This is unlike the one above. If I knew the concentration of the base, okay, then I guess the question would be over. Okay, so we're trying to figure out the concentration, the molarity of the base, knowing exactly how much acid I have. So I need to start with how much acid. So I'm going to start with 0.6745 grams. Now this becomes KHP. That's what cool people call potassium hydrogen phthalate. All right. Now, they're very nice to us, or I was very nice to you. You're welcome. That they gave us the molecular mass. And so there is what? 204.22 grams per 1 mole. All right, and of course our grams go bye-bye. And what do we know? Well, party people, for every 1 KHP, this is our stoichiometry, there is going to be 1 H plus that's given off. Okay, so the KHP goes bye-bye. So this is really moles of H plus. All right, and what do I know now? For every 1 H plus, how many hydroxides? Yeah, of course 1. It's always going to be that. And this, of course, H plus cancels, and now I have the moles of hydroxide. Now I have the amount. Pretty easy. So when I do 0.6745 divide by 204.22, essentially times by 1, I know it's silly, but please do it. It keeps everything straight in your head, especially if things do change. You get 3.303 times 10 to the negative 3 mole. Okay, and it's moles of what? Moles of hydroxide. What do they ask for? Find the molarity of the solution. So molarity, of course, is moles over the liter of the original solution, not the final solution. They want the original. Well, remember, this had H pluses in it. This has OHs. We stop the titration when they are equal. Okay, the chemical indicator they added would change a certain color to tell us it's approximately equal. And we call it the endpoint of the titration, which really approximates the stoichiometric point. Things we'll talk about, but bottom line is, what is this concentration? Well, the amount of H pluses that was the amount of hydroxide that was needed to be added to this is equal to the H pluses. So party people, in this beaker, or I'm sorry, in the burette, or I should say in the amount of base that was added, which is 41.75, that's going to be your value. So 0.04175 liters. Okay, we're after this original. We can do that because, again, we added enough base to match the H pluses. Guess what? We knew the H pluses. Okay, by measuring the amount of grams of KHP. So by figuring out our moles of H pluses, we figured out the moles of hydroxides that were needed, or that was in this amount. Remember this, you kept adding base until you stopped, until the indicator told you these were equal. All right, I think I beat that to a brown pulp. Any case, you do the math, and what you get, party people, is 7 point, let's see, carrying 4 sig fig, 7.911 times 10 to the negative 2 molar, or 0.07911. Okay, either way, it doesn't really matter. That's the molar concentration of the hydroxide. All right, so the problems aren't hard. You can see that the molarity, you can see that the mole ratios and the stoichiometry, the things we've been doing, are still now coming through. And of course, the stoichiometry, the mole ratios now are about the hydroxides to the protons. We're matching the H plus from the acid plus the hydroxide from the base, and neutralization means we're taking out the extra H pluses or hydroxides that water normally has and making water from that. All right. See ya.